are going to be taking notes on section 3.2. We're going to talk about using the lead coefficient to determine end behavior. So first thing we're going to do is, we'll just talk about an example. I think it'll be pretty clear after we do a few examples. When you're trying to determine end behavior, what you want to know is, if I were to look at the graph of this, what would be happening on the ends of each side? Where would my arrowheads be? Are my arrowheads going to be going one down and one up? They're both going to be up? Or might they both be down? So when you're asked about end behavior, that's what you're looking for. How are these going to go? What are they going to look like? So if we're looking at this particular function to determine end behavior, the first thing I want to identify is the highest degree. In this case, it's a 3. If it's odd, so if the degree is odd, then your end behavior is one up, one down. Or one rises, one falls. And now we just have to be able to determine, well, which way is it? Is it the left rising and the right falling, or vice versa? Well, in that case, I would just keep in mind this function, which you know very well, the linear parent function. And it always looks like this. The linear parent function is falling left, rising right. And that is our example for anything with an odd exponent. If it looks like this, that's the negative version of the linear parent function, y equals negative x, and it would look like this. Falling right, rising left. Because it's going up to the left and down to the right. So I can do any odd polynomial the same way. So if I were to have y equals x to the 5th, etc., 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 this is positive. So it's going to behave just like my positive linear parent function. It's going to rise right, fall left. If I were to have, for example, y equals negative x cubed, etc., 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 this is going to behave just like my negative linear parent function, which means it is going to rise left, fall right. So that's always a good way to do these. So with that in mind, if the degree on my polynomial is even, we're going to compare it to this well-known function, our quadratic, because it has an even exponent. And it always looks like this, rising left, rising right. So both are pointed up. If I were to do this and make it negative, it would be falling left and right. So anything with an even exponent can be compared the same way. So if I have y equals, let's say 5x to the 4th plus 3x cubed minus 2x squared plus x minus 7. That looks like a big polynomial, but really the only thing I'm concerned about is this. It's positive and it's even, which means it's going to behave just like my positive quadratic. So I think back, it's going to look just like this one, because this one's positive and even. So that means my end behavior is doing this, rising right and rising left. If I were to have one that, let's say, negative 6x to the 12th plus 7x squared minus x plus 10. This one looks, strange because I have this exponent of 12, but all I'm concerned about is that it's negative and even, which means it's going to behave just like the negative quadratic. So my end behavior is going to do this. It may do all manner of things in between, but the end behavior is falling left and falling right. And that's all you have to do when you identify end behavior. The next thing that we're going to do in this chapter is we are going to find zeros of a polynomial function. So if you remember back to Algebra 2 and pre-calculus, you remember that zeros are the same things as x-intercepts. If we're lucky, we can plug a function into our calculator and identify the zeros. So if this is the function I've been given, my first go-to is going to be plug it into your calculator and see if you can see them. So I'm going to go to my calculator, to my y equals, and I'm going to plug in this function exactly as it's written. So x cubed plus 3x squared minus x minus 3. I'm going to hit graph, and if I look at it, it does look like I can see 3 zeros, and I should have 3 zeros because this is cubic, which means I should have 3 zeros, and I see 3 right there, so I'm going to go to my table just to check them. Remember, your zeros are where y is 0. So there's one at -1, one at 1, and it looked like the other one was at, -3. So there's my 3 zeros. So my answer is x equals -3, -1, and 1. Those are the 3 zeros that are in this polynomial. So like I said, if you're lucky, you'll be able to find those zeros in your calculator. Now later on in the chapter, we'll figure out what to do if we can't do that. So now what we're going to do is talk about multiplicities. Zeros can occur more than once. And if you remember, we did talk about that in Algebra 2 when we referred to double roots. When we had quadratics that sat right on the x-axis and they had a double root, it meant that that 0 was really there 2 times, and you probably remember that. But now what we want to do is talk about their multiplicities. Multiplicity means how many times does the 0 occur, and this is why it's important. If a 0 has even multiplicity, for example, it appears 2, 4, 6 times. Then the graph touches the axis and turns. So if a 0 has even multiplicity, for example, it appears 2, 4, 6 times, then the graph touches the axis and turns. And when I say the axis, I mean the x-axis. So, if it has odd multiplicity, it passes through the axis. Now, in order to determine multiplicity, your function has to be in factored form. It already has to be factored. But we're going to go ahead and look at one that has already been factored, so it'll start to make more sense. So I'm going to be given a function f of x, and for example, this one is x plus 1 times 2x minus 3 squared. So I can identify that I have zeros here. There's a 0 here at x equals -1. And there's a 0 here at x equals 3/2. The multiplicity is how many times each one of those occurs. Well, I determine that by the degree. And in this case, this only occurs 1 time because there's no exponent here. So that really has an exponent of 1. This 0 has a multiplicity of 2, or it's what we would call a double root. It appears twice. So these are their multiplicities. Well, if you look back at what we just said, if I were to look at the graph of this, the graph would pass through the x-axis here and touch and turn here. So let's go ahead and plug this in our calculator and see exactly what that means. I'm going to plug it in just like this. You don't have to multiply it out. I'm just going to plug in x plus 1 and then 2x minus 3 squared. So I put that in my calculator, and when I hit graph, you can see that at my first point, -1, that was that first 0 that had an odd multiplicity, it does in fact pass through. At 3/2, which is 1.5, it had an even multiplicity, and you can see how it touches the graph and turns back around, or what we call bounces. So that's what it happens with multiplicity. If it's got an even multiplicity, it touches the graph and turns. If it has an odd multiplicity, it passes through. So let's look at another one that's already in factored form. Okay, it's already in factored form. That makes it easy to identify the zeros. So I get x equals -1/2 as one of my zeros, and x equals 5. I check my multiplicities to determine what happens at each 0. This multiplicity is even, so at -1/2, touches and turns. And at 5, it's got an odd multiplicity, so it passes through. So for right now, that's all of the notes that we will take on section 3.2. Okay, we're going to be dividing polynomials. We're going to do them by long division first. So you'll be given a problem like this. It says divide x squared plus 10x plus 21 by x plus 3. And we're going to divide it by long division just like you did in elementary school with 3 and 4 digit numbers. Since we're dividing this number, it's what goes inside the house. So I've got x squared plus 10x plus 21 inside the house, and x plus 3 outside the house. Now, when we're dividing polynomials, the first thing you want to do is disregard everything but just the first term of each polynomial. So I'm looking really at just this x and the x squared. And I just ask myself, what would I multiply x by in order to get x squared? And to multiply x and get x squared, you multiply by x. X times x would give me x squared. Now I'm going to uncover what I was disregarding a moment ago, and I'm actually going to do the multiplication. X times x is x squared, and x times 3 would be 3x. Now the next step is, I kind of think of this a little differently than I used to in elementary, but I think it makes it a little easier with polynomials. If you'll just change the signs on everything underneath and add straight down. That way we don't have to subtract, we're just doing addition. These will cancel, which is what we want to happen. And 10x minus 3x gives me 7x. And I'll bring down the plus 21. And now I do the whole process over again. So I'm going to disregard everything but just the first term of each. So I ask myself, what do I multiply x by in order to get 7x? Well, you would have to multiply by positive 7. 7 times x is 7x. 7 times 3 is 21. Change the signs on everything underneath. So whatever signs are there, you make the opposite. And add straight down. The 7's cancel, and in this case, the 21's cancel also. So there's no remainder. So my answer is x plus 7. Let's try another one. Let's divide x squared plus 14x plus 45. Let's divide that by x plus 9. So we're going to disregard everything except the first term of each polynomial. So the x and the x squared. What do you multiply x by in order to get x squared? X. Now we're going to take that x and multiply it back through. X times x is x squared. X times 9 is 9x. Now we want to change the signs on everything underneath and add straight down. My x squareds cancel. 14 minus 9x gives me 5x, and I bring down my 45. Now we go through the process all over again. What would I multiply x by in order to get 5x? That would be 5, a positive 5. Multiply it through. Again, this one's not going to have a remainder. I see as I change the signs on everything underneath and add straight down, everything cancels. So my answer is x plus 5. So that's basic long division of polynomials. Now obviously these were fairly simple because they were just trinomials. So let's do one that's a little bit more difficult. If you're given a polynomial like this, 4 minus 5x, Alright, 4 minus 5x minus x squared plus 6x cubed divided by 3x minus 2. Now the first thing that's wrong with this is that my long polynomial, the one that's going to go in the house, is not in a very good algebraic order. You must first put it in order before you put it in the house. So remember, you want your exponents in descending order. And if you're missing an exponent, for example, I have a cubed and a squared and a to the first degree, but if I were missing one, you might want to put a placeholder in because it will make your life a little easier. And we'll do one like that a little bit later. Okay, so now I'm going to do exactly what I did before. I'm going to disregard everything but just the first two terms. And I ask myself, what would I multiply 3x by in order to get 6x cubed? Well, I would multiply it by 2x squared. So now we're going to do that. 2x squared times 3x is 6x cubed. 2x squared times negative 2 is negative 4x squared. Change the signs on everything underneath and add straight down. My 6x cubes cancel. Negative x squared plus 4x squared is 3x squared. And I'm going to bring down the rest of my polynomial. Do the process all over again. What would I multiply 3x by in order to get 3x squared? I would multiply it by positive x. Multiply that through. Get 3x squared minus 2x. Change the signs on everything underneath and add straight down. What would I multiply 3x by in order to get negative 3x minus 4? I would multiply it by negative 1. So I'm going to do minus 1. Multiply through. Now I'm going to change the signs on everything underneath and add straight down. And this time I end up with a negative 6. Well, 3x, there's nothing I can multiply 3x by and get negative 6. So this is a remainder. So I'm going to write my remainder as minus 6 over the original divisor, 3x minus 2. So that's your final answer. It looks like a kind of a messy polynomial, but that's because we have this remainder of minus 6. So that's how you divide with long division. Let me do one more example where you're missing a degree and you need to add a placeholder. So let's see, we're given 6x to the 4th plus 5x cubed plus 3x minus 5. I'm going to divide that by 3x squared minus 2x. Alright, so when I go to put this in the house, I notice that I'm missing a squared term. So I'm going to put a placeholder. So I'm going to do 6x to the 4th plus 5x to the 3rd plus 0x squared plus 3x minus 5. And that really is just holding a place. It's just going to make things a little simpler for me when I go ahead and do my division. Alright, so we're going to do everything just like we've been doing before. So this will be 2x squared. I'm going to multiply back through. I'm going to change the signs and add straight down. So same process. I would multiply 3x squared times 3x. Multiply it back through. Change the signs on everything and add straight down. Would multiply 3x squared times 2 in order to get a 6x squared. Multiply that back through. Change the signs on everything, add straight down. And now when I get to here, I'm looking for what can I multiply 3x squared by in order to get 7x? And there is nothing. So this whole binomial is my remainder. So I'm going to do plus 7x minus 5 over the original divisor. And that's your final answer. So that's dividing polynomials by long division.